let's get started. So we're going to talk about sampling distributions. We've worked with distributions before, have we not? Many times. We started with frequency distributions back in chapter 2. We did binomial probability distributions in chapter 4. So now we're going to talk about a sampling distribution, okay? Which means we're working with a sample statistic. And these distributions come when you have samples of some size n, okay, that are repeatedly taken from a population. So, for example, if we wanted to collect some data about people who live in the United States, we know it's not very practical to try to collect the data from everybody who lives in the United States. So instead, what we might want to do is get some samples, all right? Now, instead of getting one gigantic sample, we might do this in intervals. Like we might get a sample that would be 100 people that come out of the state of Texas. We might want to get 100 people that come from some other part of the country. We might decide we want to get groups of people different times of the year. It kind of depends on whatever it is we'd be sampling. But the idea is we're going to get multiple samples of the same size from different places in the population, okay? Now, the one that is the most common that we're going to talk about here would be a sampling distribution of sample means. Now, you guys already know from what we did back in chapter 2, how do you get the mean of something? What's our formula? If I just give you a bunch of numbers and I say find the mean, what do? Add them up, divide by how many you have. And does it make a difference whether the numbers I give you are a population or a sample? Do you still get the same thing? The formula is the same for mean. It doesn't matter if it was a population or if it was a sample. However, if we have a big population and I were to pick samples like what you see here, where I'm going to have this sample and this one and this one and this one, is there any guarantee, in fact, do you think it's even likely that the mean of each of these samples will match exactly the population mean? No, but what do you think is going to happen if I take the mean of the sample means? If I get enough samples and I average those together, do you think it's going to be about the same as the population mean? It will, okay? It will approach what the population mean is if I average up the individual samples. I mean, one sample may be very different, but it's probably going to get offset by something else. So if I collect those, it's going to approximate the sample mean. So here's what we know. The mean of the sample means, and this is the way we signify it, the little subscript that has the X bar, because remember X bar indicates it came from a sample. So that's going to be the same as the population. That means anytime we're given information where we're working with sample means, if we know what the population mean is, we get to use it for the sample means. We don't have to go through and try to work on it by hand. Now, you know how we did have a difference, though, between the standard deviation for a population and the standard deviation for a sample, right? There was an adjustment in the formula. If you go back and you look at those formulas in chapter 2, we had to make an adjustment. We're going to do the same thing here. And so what you're going to find is, excuse me, if we were to take the standard deviation for the population, if we know what it is for the population, and we're trying to get an estimate of what it would be for the sample, you would take the population standard deviation and divide it by the square root of your sample size, okay? That's called the standard error of the mean, because remember, we're working with a sample, and that's going to make a difference with our standard deviation. If I take the standard deviation, whatever it is, and I divide it by the square root of the sample size, that's going to make the adjustment to take into account that I'm just working with a sample. It's not the population. So this is the part that I mentioned to you that with a little more time, we would probably write this out, but instead I think we're just going to view how this would work so that hopefully this will make sense to you. If I had a box up here and there were 4 slips of paper inside, one of them has a 1, one has a 3, one has a 5, and one has a 7, okay? And if I went over to Rodney and I said, would you please draw 2 slips of paper, but after you draw the first one, we're going to write down what you get, you're going to put it back in the box, and then you draw the second one, okay? So we draw, we replace, and then we draw again. We want to find the mean, the variance, and the standard deviation of the population. Now, looking at this, can you tell me what is my population? What are all the possible values that I could get? 1, 3, 5, 7. Now, how would you get the mean of the population? I do what with these numbers? Add them up and divide by 4, okay? To get the variance, do you remember the formula for variance? Let me show you real quickly in case you have forgotten. If we were to look, that was in chapter 2. And here's what we would see. Oh, please zoom in. I don't know why this is so persnickety and it doesn't want to do that. But in chapter 2, if you were to look over here at population variance and population standard deviation, since we're looking at the population, it tells us the standard deviation, we would have to do the sum of each x value minus the mean. So when we add 1, 3, 5, 7, and then divide it by 4 and get the mean, that's what we put in for our mu. That gets squared and then divided by the number that's in our population, which was 4, and we would take the square root of that. So we could plug that in and solve it, correct? Okay. Since it takes a little time to do that, we're just discussing the how instead of actually doing it. And then obviously, you would have found the variance before you got the standard deviation. So if you add 1 plus 3 plus 5 plus 7, you get 16. And 16 divided by 4 is 4. Here's your variance. If I plug into this formula, or remember, we did talk about doing it in the calculator too, because I could put 1, 3, 5, 7 in L1, couldn't I? And then I could use the calculator and I could take the sum of, what would I type in? Parentheses, L1 minus 4, because I just found the mean, close my parentheses and square it, and then divide that by what number? 4, because that's how many were in the set. And I would get the number 5 if I use that formula. And if I take the square root of 5, that would give me, excuse me, my standard deviation, which is about 2.236. So that would be the mean, the variance, and the standard deviation for the entire population, okay? Does that make sense? All right, so I'm going to give you a second if you want to write all this down. Now, it asks us to graph the probability histogram for the population values. This is actually kind of a chapter 2 type of question if you think about it. So let me take you to the sheet and let's look at what this histogram would look like. Okay? I would actually think about making a table. I put my x values here. My p of x would go here. And what were the x values I could have? 1, 3, 5, and 7. Now, what's the probability that I would draw out a 1? How many sheets had 1 on it? Out of 4. And 1 out of 4 would be 0.25. What would be the probability of getting a 3? Same thing. And for a 5 and for a 7. Now, just to remind you, when I'm building one of these distribution tables, what should all the probabilities add up to be?
1.
Exactly. So 0.25 plus 0.25 plus 0.25 plus 0.25 gives me a 1. Now, if I'm making the histogram, my x values will go here. My p of x will go here. And what were my possible values that I could get for x? 1, 3, 5, and 7, right? And for probability, since they're all 0.25, I need to put some kind of scale on here. I think I'm going to count by 0.05s. Oh, do I want to do that? I guess I can. That would be 0.10, 0.15, 0.20, and 0.25. So my bar for 1, since it has a probability of 0.25, would look like that. My bar for 3 would look like what? Same thing. For 5 and for 7. They're all the same height, aren't they? Because, well, the reason I have these where they're not touching is because it's exactly 1 and it's exactly 3. It's really more of a bar graph than a histogram because it's not continuous. There's no ability to have gotten a 2 or a 4 or any of the numbers that are in between, okay? And most of the time we did have our bars touch. That should happen on a histogram. So this is really a bar chart. But I want you to take a look at this. All the values have the same probability, which means this is called a uniform distribution, right? It's an equal chance whenever I draw it. So that's working with the population. Now, here's a different scenario. We said we were going to draw out a sheet of paper. I was going to have Rodney put it back, and then he was going to draw a second sheet. And we wanted to keep up with all of them. So if we list all the things that could happen when you draw 2 slips of paper, and we calculate the mean of each sample, okay, this is what we're going to get. This is the part that would take quite a bit of time to do by hand. But let me show you. I could draw 1, or Rodney could draw 1 the first time he draws something, and then if he puts it back, the next time he draws, he could also get a 1. Or he could have gotten a 3, or a 5, or a 7. That's the only thing that can happen if the first draw was a 1. After that, we'd have to consider what if his first draw wasn't 1? Maybe it was 3. Then he could have gotten a 3 and a 1, and a 3 and a 3, and so forth. So do you see we've got every possible combination here? We have listed the entire sample space, all of the outcomes that could happen if he's going to draw 2 slips of paper. And then what does it tell us that we need to do for each of these samples? Calculate the mean. And the mean is when I add them together and divide by how many there are. How many are in each sample? How many numbers? 2. And I have 16 different samples here. So if I were to add 1 plus 1, and that gives me 2, and divide it by 2, what's going to be the mean of this first one? Look what happens. These will be my sample means, okay? And these are the values we use to make the sampling distribution of sample means. Okay, so far, are you hanging with me? So we've listed everything that could happen if I've got a population and I want to draw some samples from it. And we could have picked a different sample size. We just picked the easiest one because this will be the least amount of work. So we've taken size 2 samples. This is everything that can happen, and we've gotten the mean of each of those samples. Now, what do you think we might want to do with these sample means to compare to the population? What did I tell you that the mean of the sample means should be compared to the population mean? It should be the same. See what happens. You guys got your calculator? I want you to see what happens if, well, actually, let me show you this first. Could we make a distribution table to go with this? You know what I'm saying? what are the possible things that I could get if I were to find the mean of these values? What are the different means that I get? Look at your numbers in red. The smallest one is 1, and it goes up to what? 7. It goes all the way up to 7, doesn't it? Okay, so I'm going to show you what we could do, and we're going to need to refer to this, so I'm going to have to do a little back and forth for a minute. So if I were to make this probability distribution table, what I'm going to need to do is to look at how many times did I have a mean that was 1 out of those samples. Do you remember? It only happened 1 time. Out of how many different samples did we have? 16. Okay, so I'm going to put the probability there. Now let me go back so you can see. Oops. Okay, so let me go back so you can see these, and you're going to do the calculations on the other. How many different times does 2 show up in this list of means? So you'd have 2 out of 16. That's going to be your probability that you get a mean of 2. What about 3? I see 1, 2, 3, 3. So 3 out of 16. That's the probability that the mean would be 3. Can you calculate the rest of these? Everybody following what I'm doing? All right, so I'm going to let you see if you can finish out the table with the probabilities. Okay, so is this basically how your chart ended up? Do you have 1 over 16, 2 over 16, 3 over 16? The most that occurred was 4. It occurred 4 times out of 16. And then did it start counting back down? So 3 out of 16 for 5, 2 out of 16 for 6, and 1 out of 16 for 7. And so we turned those into decimal form. If we added them all up, what does it equal? It equals 1. Very good. Now, if you look at the next slide, here's what it asks us to do. We just did the probability distribution, which is what you guys came up with. We didn't include the frequency column in the middle, but we did put what the means were and what the probability was of getting those means. And now they want us to find the mean, the variance, and the standard deviation of the sampling distribution of the sample means. Now, here's what that means. I now have a frequency distribution, right? A probability distribution where I've got the different means and the probability that those would occur. What's the formula for finding the mean if I have a table with an x and a p of x? The sum of x times p of x. So in other words, if we wanted to use the calculator, what could I put in L1? Exactly. I could put these values in my L1, the x bars, and then in my L2, I would want to put these probabilities. And then it's just a matter of using my formulas to see what the mean, what the variance, and the standard deviation would be for this sample set. Are you guys following what I'm saying? Okay, we have made ourselves a probability distribution. This is like, I mean, we did frequency distributions back in chapter 2. In chapter 4, what we just tested over, we did probability distributions, and they're very, very similar. So all you have to do is take the sum of x times p of x, and that will give you the mean of the sample means. Anybody got it all in the calculator and done it yet? Are you guys with me? I can't tell if I've lost you. Okay, so if I go into Stat, Edit, I'm going to put in 1, 2, 3, 4, 5, 6, 7 in my L1. And then in my L2, I'm going to put in these probability values that we found. So 0.0625, 0.125, 0.1875, 0.25, 0.1875, 0.125, and 0.0625. Okay, so they're in my calculator, and we said to find the mean, we would do what? Sum of L1 times L2. So if I were to take second stat and go over to sum, which is number 5, and I tell it to multiply L1 times L2. Ta-da! What number is that? Which is the same thing that our population mean was, correct? That is to illustrate to you that when we're working with those samples, the mean of the sample means will equal the population mean, okay? So we don't have to make any adjustment to mean if they have given us the population mean and we're working with samples. Now, the formula for standard deviation is what? Again, we'd go to second stat, we'd choose sum, or actually let's do variance first, because variance is L1 minus, what did we get for our mean? 4, and that gets squared, and then we do what? Times L2? Isn't that how we found the variance? All right, I want you to notice we got 2.5. That would be the variance for our sample means. And then what would we do to get the standard deviation? Are y'all getting something different? Y'all are so quiet. Have I lost you? Where are these formulas coming from, guys? Look right here. This is where they're coming from, okay? You know, let me take a second here and see if I can. It needs, oh, there it goes.
Oh, that's much.
So sorry. It's very finicky. Sometimes it will zoom and sometimes it won't. So I'm glad it finally zoomed in. Okay, so all we're doing is using our formulas to be able to calculate these. And then the difference between the variance and the standard deviation is you do what? Take the square root. So all we have to do is take the square root of 2.5, and that's going to give us what our standard deviation would be for these population means. Okay, we together? Then let me show you something. This is using the shortcut, okay? We did it by hand, but did we just find that 2.5 was the variance using our formulas and taking every one of those sample means and the probabilities and putting them in the calculator? Yes, and the square root of 2.5 was 1.581, okay? Now, here is the shortcut. You remember, if we go back to, let's see, right here. Look what it said we could do to get the standard deviation for the sample means. If we took the population standard deviation and do what with it? Divide it by square root of n. That's going to be a shortcut. Now, look at this. Let me get back where we were. Okay. If we had taken our population standard deviation, which was the square root of 5, remember? Because we had for the population, the variance was 5. That meant the standard deviation was square root of 5. Guess what the square root of 5 divided by the square root of 2 is? 1.581. It matches. Is that a faster, easier way to come up with these values if we need the mean and the standard deviation and the variance of a population of sample means? And we already knew what the population was. I would think so. So if you look on your formula sheet, and let me take you there real fast. Okay. Here in chapter 5, because we're at the end of chapter 5, that's where you're going to see this adjustment right here. If you need to take the variance of a sampling distribution, it's got to be the population variance divided by whatever n is. And then if you needed the standard deviation, you just have to take the square root of that, right? Okay, so those are there if you need them. They're faster, easier ways rather than trying to reinvent the wheel and put everything in your calculator and do it by hand every time. Does that make sense? Okay, I figure you like shortcuts. Now, let me just show you on this. If we were going to graph the probability histogram for the sampling distribution of sample means, can we do it? Because we've already made the probability distribution, right? So to save a little time, let me just show you what it looks like. You can put this on your paper, on that part that's asking for the histogram. All we're doing is making sure our scale reflects probability accurately. So if I did from 0.05 up to 0.25 on the probability, look at this. I've got 0.0625 is my probability for getting a 1 as a sample mean. When we got to 2, the probability went up to 0.125, and this one was like 0.1875. There's 0.25, and then it comes back down. Tell me what you noticed about the shape of this thing. There you go. It is symmetric. It is bell-shaped, so that means it approximates a normal distribution. Now, did the original look like a normal distribution, the population? It was uniform, wasn't it? But based on this sample, where we're taking out 2 slips at a time, the sampling distribution of the sample means is a normal distribution. Now, that leads us to something that's very important, and it's used a lot in statistics. It's called the central limit theorem. And this is the concept. Up until this point, when we were working on things in chapter 5 on this last test, in order for us to be able to use the bell-shaped curve and use those z-scores and all that kind of stuff, we had to see what words? You remember? It said it had to be normally distributed, correct? If it wasn't a normal distribution, it wasn't one of those chapter 5 problems. Well, here's the interesting thing. We just saw that the original was not a normal distribution on this problem, but when we took the sample of the means, we had a sampling distribution of sample means, it was normally distributed. So here's what the central limit theorem says. As long as my samples have at least 30, n is greater than or equal to 30 in my sample size, as long as it's that large, drawn from any population, even one that's not normally distributed, okay, then here's what I know. The sampling distribution of sample means will approximate a normal distribution. And the greater the sample size, the better the approximation. So what is the minimum number that has to be there for me to use the central limit theorem? 30 in my sample size. If it says that I have sample size of 50, does it matter if it tells me that the original was a normal distribution or not? No, I get to use the central limit theorem, and it means that the properties of a normal distribution will apply to my sampling distribution of sample means. Now, here's what else we need to know. If I know the population is normally distributed, Does it matter how big the sample size is? The answer is no. As long as the population is normally distributed, then the sampling distribution of sample means will be normally distributed for any sample size. So if you see the words normally distributed, it's okay if the sample size is less than 30. You can still know that the central limit theorem applies because you started with a normal distribution. If it doesn't tell you you have a normal distribution to start with, then you have to have sample size of at least 30, or you're kind of stuck. You can't do anything. Okay? So far, so good? Now, doesn't matter which case I have, will the mean of the sample means, the sampling distribution of sample means, will that mean be the same as the population? Every single time I get to use the population mean to go with my sample means, okay? But I make an adjustment to the standard deviation. And that tells me that I have to take the variance of the population and divide it by n, okay? And so, in other words, that would be for the variance. If I'm doing the standard deviation, I've got to divide it by the square root of n, okay? Now, we'll look at some examples of this so you can see. But basically, I'm making the adjustment to the variance by dividing it by n. Since the standard deviation takes the square root, it means I've got to divide it by the square root of n. And this is typically called the standard error of the mean when we're talking about the sampling distribution of sample means. But it's really the same thing as the standard deviation. They just give it a special name because it's working with the sampling distribution. Okay. So if I have any kind of population, doesn't matter if it's normally distributed, I can take the distribution of sample means and assume it will be normally distributed as long as my sample size is at least how many?
30.
30. All right. This is kind of the whack-a-mole portion of tonight's course. I'm making sure you guys get this number down in your brain. As long as it starts as a normal distribution, does the sample size matter? No, but either way, notice we still adjust the standard deviation because we're working with a sample, okay? Now, let's apply this. It says cell phone bills for residents of a city have a mean of $63 and a standard deviation of $11. Random samples of 100 cell phone bills are drawn from this population. The mean of each sample is determined. Can we find the mean and the standard error of the mean of the sampling distribution and then sketch a graph of the sampling distribution of sample means? Okay, so here's my question. Does it tell us that the original distribution is normally distributed? What do you think? Do you see in there where it says that the original distribution is normally distributed? No, it gives me a mean and it gives me a standard deviation, but it doesn't say anything about a normal distribution. Is this going to be a candidate for using the central limit theorem?
Yes.
Very good, because my n is 100, right? Because it's a sample of 100 cell phone bills. Now, if that's the case, what do I know about the mean of the sample means? It's got to be the same as the population, so it's $63. That's the easy one to answer. What do I know about the standard deviation of the sample means or the standard error of the mean? How do I find that? If you need to, look on your sheet. How do you find that? Is it the same as the population standard deviation? Is it? Oh my goodness, look right here.
Is it divided by the square root?
That's it, right there. If we're working with the sample means, then the standard error of the sample means is the standard deviation divided by the square root of n. So according to this, the standard deviation for the population was how much? $11. And we're going to divide that by the square root of what number? And the square root of 100 is? Yeah, is 10. And so 11 divided by 10 is 1.1 or $1.10. Does that make sense? Okay. Now it says sketch a graph of the sampling distribution of sample means. Because of the central limit theorem, do I know what shape this graph should be? It's what? There we go. It's bell-shaped. And the mean is what? $63. My standard deviation, we said, was $1.10. Okay, now, in terms of putting some sort of scale on this, think about what we know from the empirical rule back in chapter 2. If I were to move one standard deviation from the mean, that's about what percent of the data? Yeah, it's like 68% or so. If I go 2 standard deviations, I'm up to what? It's like 95, isn't it? And 3 is 99.7. In other words, I'm like way out here in the tail. Okay, let me kind of fix that a little bit. So I've got just about everything 3 standard deviations away. So if my standard error of the mean is $1.10, that would mean if this is 63, then if I add $1.10, I'm at $64.10. This would be $65.20. This would be $66.30. In other words, I could adjust my scale to indicate that by the time I'm out in the tails, 3 standard deviations away, I've pretty much gotten everything. Okay? Now, let's look at how they did their graph. It's a little, they made theirs a little tighter instead of as spread out as mine is. But we do have the same information for mean and standard error of the mean. They just made their scale so that everything was clustered really tight next to 63. So if you were having to sketch it out, you just need to make sure you've got something that would make it clear how your values are distributed. All right, now look at this one. Suppose the training heart rates of all 20-year-old athletes are normally distributed. The mean is 135 beats per minute. Standard deviation is 18 beats per minute. Random samples of size 4 are drawn from this population, and the mean of each sample is determined. Find the mean and standard error of the mean, and then sketch graph. All right, is this one a candidate for the central limit theorem? Why? There you go. Very good. Even though the sample is size 4, it tells me the population is normally distributed. So it doesn't matter how big my sample is. Good job. Okay. Now, looking at this, let's see if you can come up with what the mean should be for our sample distribution of sample means. What's it going to be? Yeah, because it's got to match this one. So it's going to be 135. Now, can you calculate what would be your standard error of the mean? The n is going to be 4. Mm-hmm.
And 18.
Yeah, and 18 is what the population standard deviation is. Now, I know on the last one, we got a decimal number. Are we going to get a decimal on this one for the standard error of the mean? Hannah says no. Do y'all think she's right? What do you get? Very good. The answer is 9. Here's why. If we were to take 18 and divide it by the square root of 4, is 4 a perfect square? Square root of 4 is 2, and 18 divided by 2 is 9. So those are the values you should have for the mean and for the standard error of the mean. Now, as far as sketching a graph, you get to decide how you want to show the distribution. This is an example of how it might look. If I get 3 standard deviations away, 9 times 3 is how much? 27. So if I were to take 27 away from 135, I'm going to be at like 108. All right, so they didn't even mark off necessarily, but they're just giving enough perspective that you can see by the time you're 3 standard deviations out, you're in a tail. Got it? Okay. Now, we can also take these X bar values and change them to Z-scores. We might have a need to do that at some point. We know in the last test, sometimes we had to change X's to Z's. So we know the formula for calculating Z is X minus mu divided by what? Standard deviation. If we're talking about working with sample means, and this is the standard error of the mean, that means instead of using the population standard deviation, we have to divide by, yes, so it means you take that population, divide it by the square root of how many are in your sample. In other words, you got to use that adjusted standard deviation, and then you can convert it into a Z-score. Make sense? Okay, and if I'm converting it into a Z-score, the only reason I maybe would need to do that is if I'm looking for the probability of maybe a sample mean being less than some value. And I've got to change it to this so I could look it up in the table, or, sounds like we might have another option. What else did we do when we wanted to get probabilities of some number being to the left of something? What did you do on the last test, those of you who use your calculators? A normal CDF. We're going to have the option to do that too. And it's the same thing we did on the test, except remember the last thing you put in the normal CDF is the standard deviation. We just have to make sure we make the adjustment for the standard deviation if we're using the central limit theorem. So far, so good?
That second one, is that saying like it's this, but it's also this, but it's also that?
Yeah, this is saying if I'm looking for the Z-score, the formula means take whatever value you're trying to change and subtract the mean, which would be, remember the population and the sample mean is the same. That's what this part is saying. And divide it by whatever that standard error of the mean is. So if they give you some sort of value for the sample that they're asking you, what would be the probability of some number being less than this, we would plug into this formula to get it. Okay.
The whole table is just saying.
Correct. It's just, yeah, it's just kind of replacing pieces with a different way of writing the formula. So this is kind of an interesting graphic, and I say that to give you the heads up. Pay close attention because it is tempting to kind of get lost and look at the wrong thing. So here's what it shows is the average time spent driving each day by age group. So if you're in the age range 15 to 19, not that much. You're probably just going back and forth to school. 25 minutes. 20 to 24, 52 minutes spent driving. 25 to 54, 64 minutes. And then it starts to come back down a little bit the older you get. 55 to 64 is 58, and then 65 plus is 39. So here's what we're going to do. It says you randomly select 50 drivers ages 15 to 19. What's the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? And then they tell us what the population standard deviation is, which is 1.5 minutes. Okay? So do you kind of understand what it is we're going to look for here? I'm looking for the probability that the mean time that they would spend driving in this sample is going to be between 24.7 and 25.5 minutes. Okay? So tell me something. Do I have a central limit theorem problem here? What do you think?
Yes.
Okay, and the reason you're saying that is why?
50 degree.
Because did you see the words normally distributed anywhere?
No.
So if I didn't see that, the only thing I can do is make sure the sample size is greater than 30, and then I can assume that my sample will be normally distributed. So because of that, I will say that my mean of my sample means is going to be what? And this is the sneaky part. You need to look at your graphic and see if you can tell me. And that came from where? You're exactly right, Lindsay. Do I even need any of these other pieces of information? No, that's the sneaky part. My sample involved only drivers that were ages 15 to 19. So that would mean that 25 minutes is going to be the sample mean, okay? Now, I do need to get the standard error of the mean. And how do I calculate that? If you need to, look on your formula sheet. It's got to be what?
Standard deviation.
Standard deviation divided by what? Square root of how many are in my sample. So my standard deviation is 1.5. And then what was my sample size? Excellent. So I got to divide that by the square root of 50. All right, tell me what you get when you do that. Okay, I've got a vote for 0.2121. Y'all agree? Sounds good to me. Okay. So, have I answered my question yet? Nope, because what's it asking me to find? The probability that the mean time spent driving in this sample would be between 24.7 and 25.5. You guys said this is going to approximate a normal distribution. And if the mean is 25, then I want to know between 24.7 and 25.5, what is that probability? Oh my gosh, what does that look like to you? Do you have the tools now to find it? I think so. Now, if you're using your table and looking at z-scores, you got a lot of work to do to convert these z-scores, don't you? So you'd have to take the 24.7 minus 25, divide it by what we just found for our standard error, the mean, to get that z-score. Have to do the same thing for the 25.5. Then you can look those values, those z-values up in the table and subtract. Anybody interested in the normal CDF? Okay, here's what we would do with that. I'm going to go into second bars, and I'm going to choose normal CDF. And according to this, my lower is going to be 24.7, correct? This is the nice thing. I don't have to change them to z-scores. I can keep them as x-scores. What would I put in for upper? 25.5. What would I put in for the mean? 25. What do I put in for my standard deviation? Very good. You can either put in the 0.2121, or if you wanted to actually type in 1.5 divided by square 50, it'll adjust it for you. We'll just put in 0.2121. Wow, that's a pretty high probability, isn't it? So, because if we were reading this out of the table, we'd go how many places to the right? 4. This is going to be a probability that this X bar value is between 24.7 and 25.5. That's going to be 0.912 what? 22. If we go 4 places to the right. Is that making sense? All right, let's see what our PowerPoint says. Because they're going to show us, if you look it up in the table, that's going to be the z-score values you would come up with. And then if you take these and subtract, they've got 0.9116. We're actually within 0.0006. It's off a little bit more than I would expect. But actually, which one is probably more accurate? Ours, because they're using lots of rounded values, changing everything to z-scores and looking it up. But again, that's going to be one of those that I'm going to work with you on that if you do get something different using the calculator versus what you would get out of the table. All right, look at this. An education finance corporation claims the average credit card debts carried by undergrads are normally distributed with a mean of $3,173, standard deviation of $1,120. Now, some of you guys, you're still pretty young, haven't been out of high school that long. Do you get bombarded with credit card applications in the mail? Okay, some people do, and I always try to caution my dual credit kids, man, be careful, because you can get yourself in a world of hurt in a hurry if you're not careful about this. So think about this. If you're talking about undergrads, you're probably talking about a pretty young population, and they're saying that their average credit card debt is $3,173, okay? And the standard deviation is 1,120. Now, could we determine what the probability is if we randomly select a single undergraduate student who is a credit card holder? What would be the probability that their credit card balance is less than $2,700? Do we have the ability to figure that one out? Do we know how to do this even before tonight? Yes, because it is for a single value. We want to know the probability to be less than that. And what words do you see that are important if I'm trying to find the probability? Normally distributed. So let's look at how we would calculate this, because there's not a sample involved here. It's just a single person. We want to know what would be that probability. So since it's normally distributed, I'm going to sketch my normal curve. What did it tell me the mean is? My standard deviation is 1120. And I want to know what's the probability that their balance is less than $2,700. Somewhere over here. Does that look like either converting to a z-score or doing a normal CDF problem to you? Yeah, so if I wanted to do a normal CDF, now remember, anytime we're working in a tail, we got to be careful that we put the adjustment in carefully. So if I go to second bars, normal CDF, I don't know exactly how far out I need to go for this tail, so I can put some really small number like negative 10,000 and I should be good. What would I put in for my upper value? 2,700. What's my mean? 3173. And then for my standard deviation, what do I put in? Good, because I'm working with this population. I'm just getting the probability that one person pulled at random would be out in this tail. What does that tell me? I get the probability that they owe less than $2,700 on their credit card to be 0.3364, or almost 34%. Okay? Would you say that's a not terribly unlikely event? I mean, 34% likelihood, that's not bad. Okay? Now, look at the next question. You randomly select 25 undergraduates who are credit card holders. What is the probability that their mean credit card balance is less than $2,700? Is that the same problem? No, because what do you notice is involved here? It's a sample of 25. Does this qualify for the central limit theorem?
Yeah, it is.
Yes, it does. How come, Rodney?
Because originally it was normally distributed.
There you go. The original distribution is normally distributed, so it didn't matter what my sample size is. but I still have to make adjustments. So I keep the same mean, which is 3,173, but what do I have to do to the standard deviation to adjust it? Is it the same as the population, which was 1120? No, I have to do what to it? Divide by the square root of 25, because that would be how many were in the sample. So if you take 1120 and you divide it by the square root of 25 is 5, you get 224 for your standard deviation. Does that make sense? Okay. Now, I still have 2,700 somewhere over here, and I'm trying to get the probability that the mean credit card balance of these 25 people I have selected at random would be here, okay? So how do I calculate that? Is that also a normal CDF? But what's the only thing that has to change? No? The standard deviation, exactly. If we go back in to normal CDF, I'm still in the left tail. I'm still using an upper value of 2,700, but my mean is the same, but now my standard deviation ends up being 1120 divided by 5, which is 224. What's the probability that this would happen? Yeah, 0.0174, less than 2%. Now, that's a big difference. Would you agree? Is it logical when you think about it that if I've got 25 people in my sample, that their mean credit card debt, the average of their credit card debt, would be less than 2,700? You see why that's so different from one particular individual? I'd have to have kind of, in fact, would you say this is an unusual event if it occurs? Yes. So we're almost through with 5-4. And that's what we got on the first one. And this is what we got whenever we calculated for the sample of 25. Okay. And so here's how they sum it up. There's about a 34% chance that an individual undergraduate would have a balance of less than $2,700. But there's only about a 2% chance that the mean of the sample of 25 would be less than that, which definitely makes it an unusual event. Now, here would be the conclusions you could draw. It is possible you just get a really unusual sample. You just happen to get a lot of people who are really on top of their credit and didn't have nearly as much debt as most people. Or is it possible the corporation may not be truthful in saying that the mean is 3,173? That could be an incorrect value that they proposed. But one of those two would tend to be true. I've either got an unusual sample or I've got bad information. All right, and that is everything that is in 5-4.